All right, so this is our next and maybe final lesson in this concept of estimating the area under the curve of a function. And so the question might say, estimate the area under the curve of y is equal to x squared over the interval from 1 to 4 using 6 left endpoint rectangles. And kind of where I want you to be at this point is for you to see this and to think in your head that we're going to be taking this function. I'm not even taking the specific function yet into account, but I know it's going to have a left endpoint of 1 and a right endpoint of 4. And then I want to split that up into 6 equal sections. So how would that be? Let's see. And this is 1, 2, 3, 4, 5, 6. Okay, so those are 6 different rectangles, and you can kind of think of this as x sub 1, x sub 2, up to x sub 6. And then in your head or on your paper, you want to think of what the width of those rectangles is. And what you want to do is you want to think of the total distance, which is 4 minus 1, and divide that by 6. So that's 3 divided by 6, which is equal to 1/2, which means I'm going to be looking at rectangles that are spaced out by a half. And still, I still haven't even looked at the function. What I know is that I'm going to have a set of, to estimate this with 6 left endpoint rectangles for each rectangle, I'm going to have to, so there's going to be a function that does something, and I'm going to have to go up to wherever it is on the left endpoint, and I'm going to have to draw a rectangle. And we know that this function is increasing, so we can kind of see that it's going to be an underestimate. If I'm thinking what the calculation will be, it's going to be 1/2 times, well, what's the height of the first rectangle going to be? Well, that's just f of 1. Plus, what's the height of the second rectangle going to be? That's f of 1.5. Plus f of 2 all the way up to, what's the last one going to be? That's going to be 3.5. And then you should know that to figure out what f of 1 is, well, f of 1 is just going to be 1 squared, which is 1. F of 1.5 is going to equal 1.5 squared, which is 2.25. And you could go through and you could do all those calculations. And actually, in a typical school year, we spend more time at developing your proficiency and being able to do those actual calculations, and it is helpful. So I would suggest that you pause the video and come up with an estimate for what the area under the curve is using 6 left endpoint rectangles. Using a pen and a paper, maybe like a little cell phone calculator, but not a tool like Desmos or a graphing calculator that'll actually do the summation part for you. And do it for right endpoint rectangles too. And then come back when you have it. And I'm not going to give you the answer yet. I will give you the answer in a little bit. I'm not going to actually do all that stuff because I've graduated from doing all that hand calculation type stuff, and now it's more into just symbolic representation. But if we try to think of a nicer, neater way of writing this, because we might end up having more than 6 rectangles, and this gets to be a little bit tedious. We have this symbol that we've also introduced that means summation. And there is a way to use it to save you work or save you writing. If you think of what is this going to be? Well, this is going to be the sum of 1/2 times what? Well, I want to go f of 1 plus every time this counter goes up. So this counter is going to start at 0. And it's going to end at this spot right here, x of 5. So it's going to go from k is equal to 0 to 5 of f of 1 plus 1/2 times k. And You may not be at the point where you can just come up with that like I just did, but I want you to be able to see, if you think of what this thing would actually do, well, k is going to start at 0. When k starts at 0, you're going to have f of 1 plus 1/2 times 0, which is f of 1. Look, that's where we started at. Then k is going to jump up. It's going to go to 1. So when k is equal to 1, what's going to happen? You're going to have 1 plus 1/2 times 1. That's 1.5. You're going to have f of 1.5. Boom. That's what we have in our second calculation. What's going to happen after k takes a value of 1? It's going to take a value of 2. When you plug in 2, you get 1/2 times 2 is 1. 1 plus 1 is 2. So I'm going to be valuing f of 2. And you should be able to see, if you need to look at it more slowly, that this is equal to this. In that there's some bit of generality in this one that I've written in both of them that have not taken into account the actual function that we have here. The actual function that we're dealing with is x squared. So I could also call this 1 plus 1/2 k squared. And I could evaluate that. And if I did that on Desmos, that should give me the value that you calculated here. So let's say SUM, n goes from 0 to 5 of 0.5 times 1 plus 0.5 n squared. And I get 17.375. But you might say that's not that great of an estimate. I still want to keep doing this stuff. It's fun. Or you might say that I know that that's an underestimate. I would like to have not only an underestimate, but I'd also like to have an upper estimate so that I can have a confidence interval. In which case you might say, since that was a left endpoint rectangle, the overestimate is going to be right. So what happens when we go to right? Well, if we go to right endpoint rectangles, we're not starting from the left endpoint. We're going to start from the right endpoint of each rectangle. Okay, so which x values am I using? I'm going to be using x sub 1, x sub 2, x sub 5, and x sub 6, which means my formula is going to look like 1/2 times f of 1.5 plus f of 2 all the way up to f of 4. If I want to write it in summation notation, it's kind of convenient because only one thing changes, and that's the value that I start k at. Instead of starting k at 0, I'm going to start k at 1. And I'm going to go, instead of to 6 minus 1, I'm going to go all the way up to 6. And if I go back to Desmos, and I got 24.875. So you might think that that's cool because now I can estimate the area. The true area A is somewhere greater than 17.375. And it's less than 24.875. And so then you might think, well, what if I wanted a more accurate answer? Which we always want a more accurate answer. And we have the capacity to get a more accurate answer. The only thing is, to get a more accurate answer, it gets a little bit more tedious. Because what is the thing that I'm going to say? Well, let's go back to where we started with 6 left endpoint rectangles, and let's do more. Let's do, for example, 9 endpoint rectangles. And let's make kids do more tedious calculations, because that's what gives us satisfaction in our job, which we're lacking in these times of shelter in place. But you may also realize that there's tools online that help you calculate some of these things. So in your head, thinking, if I'm going to increase this number of rectangles from 6 to 9, you might think, what's the width of each rectangle going to be? And then it's going to be 1/3. And what I'm interested here is more of you just kind of understanding what's going on conceptually. When we increase the number of rectangles, watch what happens. This is my left endpoint rectangle. When I go up to 9, now the area that's in between the rectangles and the curve gets smaller in each case. The amount that we're off by is less. So if I increase to 9, remember at 6, my region was from 17.375 to 24.875. If I go to 9 rectangles, I'm going to get from 18.56 to 23.56. So the region got smaller. Okay? Our error got smaller. You might be like, why 9? Why stop at 9? Let's go to 12. Why stop at 12? Let's go to 20. Why stop at 20? Well, the only reason we're stopping at 20 here is because that's the only thing that this interactive applet lets us go up to. When we go at 20, we're at 19.88625 for the left hand, the underestimate, and we're at 22.13625 for the upper estimate. And there's this thing over here that says the exact integral of this function, which this is like one of those things that you learn in calculus. You don't really learn this in pre-calculus, what the integral means. And if you do, it's at the very, very end of this course. But it's kind of like we're in pandemic and parents are letting kids watch things on Netflix that they wouldn't otherwise just because they have to. And I feel like it's the same way with calculus. Since we're in a pandemic, I'm allowing you to understand a little bit about what this integral sign is, because that's really the goal of all this idea anyways. So what I want us to think about, this is going to get to be a little bit long, but is what happens if I go super abstract and I say just estimate the area under the curve y is equal to f of x over the interval from a to b with n rectangles using left endpoints. And I'm just going to go straight to the summation notation. And what would it look like? Well, for each of those rectangles, I need to know the width of the rectangle. So that's going to be b minus a over n. You can sort of think of b minus a over n as this width, like the amount that the function is jumping each time, or delta x. We'll come back to that, but I'm going to say b minus a over n is the width of the rectangle times what's the first rectangle that I'm going to have to start at? Well, I'm going to start at whatever a is, and I want to build in a mechanism that jumps up by the width of the rectangle each time. So b minus a over n times k, where k goes from 0 to, well, when we had 6 rectangles, we went to 5. So we're going to go from 0 to n minus 1. And I know there's a lot in that formula. It's very abstract, but keep in mind that if I think of just this part as the width of the rectangle, delta x, it gets a little bit more legible. And then if you think of what happens if I switch to right, well, not much changes, okay? I can literally just copy all this And I'm going to go k is equal to 1 to n. And are these things the same? Well, they're not the same. We saw in this picture that they're not equal to each other, but we did see as n increases, they become closer and closer to each other. So this is like it. This is the final thing that bridges the gap from this concept to one that's calculus. And in calculus, what calculus is really a science of, it's dealing with things as they get infinite. Things can be infinitely big or infinitely large, infinitely big or infinitely small. But we're thinking of this as, what is the limit as n goes to infinity of the left endpoint rectangle? K is equal to 0 to n minus 1 of, I'm just going to call this delta x f of a plus delta x sub k. Well, hopefully you can agree that that's the same. This theoretical concept of a limit is going to equal itself, or is going to equal the left endpoint and the right endpoint. So the limit as n goes to infinity from the left endpoint is going to equal the limit as n goes to infinity of the right endpoint. Again, this is left and this is right. And this is what we call this integral figure, this integral from a to b of f of x dx. And you don't have to know that yet, but you will have to know it for calculus, and we will come back to this towards the end of the year, where, just so you know, the triangle is pronounced delta. That's what becomes delta x. This sigma sign is a summation. That's where we get the integral sign that looks like a big S for summation.